We have seen symmetric kernel, and we have defined the um, pronoun operator, adjoint operator, the symmetric kernel, some properties of symmetric kernels, L2 function, then the iterated kernel, some results I told you to prove. Okay, now today we will see some results of the symmetric kernel. Some I will prove, some will be left as exercise that we should complete. Okay, now first result, right? Result, the eigenvalues. We have seen the definition of eigenvalues, eigenfunctions of the kernels of the integral equation. The eigenvalues of symmetric kernel are real. So whenever we have a symmetric kernel, then always remember the eigenvalues of that symmetric kernel are always real. Let us prove this. Now let us take our symmetric kernel. So let k x comma t be symmetric kernel, and let lambda with eigenvalue of k be the eigenvalue of the kernel k. And we have this eigenvalue. Let us take the eigenfunction and let y of t be corresponding eigenfunction. So if lambda is the eigenvalue and y of t is a corresponding eigenfunction, this implies y of t has to be equals to lambda integral a to b k x comma t. Let me take y of x here. Y of x is equals to integral from a to b kxt yt dt, and this we will write it as lambda k y of x. Okay. That is, this will be y of x minus lambda k y of x will be equals to 0. Now for this we multiply by y star of x. We get, you multiply this equation by y star of x, it will be y of x into y star of x minus lambda k y of x y star of x equals to 0. And now you integrate from a to b. Integrate from a to b. When you integrate, you will have integral a to b y of x y star of x dx minus lambda integral a to b k y of x y star of x dx is equals to, you remember this is the integral, ky of x is the integral, that's what we have denoted. This is nothing but norm of y the whole square, and this is nothing but minus lambda inner product of ky with y, and that will be equals to 0. And when you simplify this for lambda, we get lambda is equals to norm of y the whole square divided by inner product ky with y, and of course this belongs to R as A is symmetric kernel. This is real, and if K is symmetric kernel, we have already proved that this is symmetric. This is real. That means this lambda will be a real number, and this completes your proof. So always remember, if you have a symmetric kernel, then its eigenvalues are always real, right? If you have a symmetric kernel, the eigenvalues of a symmetric kernel are always real. Okay, let me state a race features theorem that we already seen in your functional paper. Race feature theorem. This you may have to use in the proving next results. I will leave this as exercise as well. Now here, if phi I of x is a sequence is given orthonormal system of functions in L2 space. You take L2 space and you take a orthonormal system of functions phi I of x in that L2 space, and let alpha I be a given sequence of complex numbers such that the series from 1 to infinity mod of alpha I square converges, then there exists a unique function fx. Again, there is a problem of uniqueness. Unique function fx for which alpha I are the Fourier coefficients. The Fourier coefficients with respect to the orthonormal system phi I of x, and to which the Fourier series converges, in mean. That is, norm of fx minus summation I from 1 to n alpha I phi I of x. This norm will tend to 0 as n tends to infinity. As n goes to infinity, this will be infinite series, right? So it will converges in mean. So this series feature theorem you already came across in your functional. So let us prove one statement, and then the next results I will leave it as exercise. Result: the eigenfunctions, the eigenfunctions of a symmetric kernel corresponding to distinct eigenvalues are orthogonal. So, as in the case of linear algebra here, the eigenfunctions of a symmetric kernel corresponding to distinct eigenvalues. If you have two distinct eigenvalues, then the corresponding eigenfunctions are orthogonal. That's what we have to prove. So, to prove this, you take two distinct eigenvalues, let lambda 1 and lambda 2 be distinct eigenvalues of y1 and y2, right? Let lambda 1 and lambda 2 be the distinct eigenvalues of y1 and y2. Let me put it in the other way. Let lambda 1 and lambda 2 distinct eigenvalues corresponding to lambda 1 and lambda 2 with the distinct eigenvalues, and let us put that way. And let y1 and y2 be corresponding eigenfunctions. Now, since lambda 1 and lambda 2 are eigenvalues and y1 y2 are corresponding eigenfunctions, we will have y1 will be equals to lambda 1 k y1 and y2 will be equals to lambda 2 k y2. And we have to show that the eigenfunctions are orthogonal. The distinct eigenvalues are orthogonal. The eigenfunctions of a symmetric kernel corresponding to the distinct eigenvalues are orthogonal. So our claim is inner product of y1 and y2 is 0. Okay. Now since lambda 2 is real, both lambda 1 and lambda 2 are real, and we have this y2 is equals to lambda 2 k y2, that is we have this y2 of x is same as lambda 2 integral a to b k x comma t y2 of t dt. And when you take complex conjugate and lambda 2 is real, we implies this y2 bar of x will be same as lambda 2 integral a to b, because lambda 2 is real, bar is same as lambda 2 k bar of x comma t y2 bar of t dt. And since our kernel is also symmetric, since kernel is symmetric, we have y2 bar of x the same as lambda 2 integral a to b ktx y2 bar of x y2 bar of t dt. and you change the variable now, you will get y2 bar of t will be equals to lambda square, not lambda square, it's lambda 2. Lambda 2 integral a to b k dx. We are changing the variable, so kxt, you put x as t and t as x, y2 bar of x dx, changing variable. Okay, now also we have y1 of x is equals to lambda 1 integral from a to b k x comma t y1 of t dt. Remember your aim is to show that the inner product of y1 y2 is 0, that is integral of y1 y2 is 0. That's your aim. Okay, now we have y1 of x is equals to this, because this lambda 1 is a eigenvalue and y1 is a corresponding eigenfunction. Now you multiply both the sides, multiply both sides by y2 bar of x and integrate with respect to x. Integrate with respect to x, will have, you first multiply by y2 bar of x and then you integrate, so integral a to b y1 of x y2 bar of x dx, that will be equals to this lambda 1 is there. Let's keep this integral a to b, then write this integral here, integral a to b k comma t y1 t dt, and then you multiply this by, right here, y2 bar of x dx. So this integral in the bracket is from here, this lambda 1 is outside, and then this integral and this y2, when you multiply you are getting that. Okay, let's go on the next page. This will be equals to lambda 1 integral a to b. Now you change the order of the integration, so integral from a to b, integral from a to b k x comma t y2 bar of x, you change the variable of this order of integration, dx y1 t dt by changing order of integration. This will be equals to lambda 1 integral a to b, and this bracket is nothing but 1 upon lambda 2 by 2 bar of t, and this is y1 of t. Okay, let me tell you why it is. Now when you see this bracket, this will be out over here, here. So integral from a to b kxt y2 bar of t dt t is this, and you substitute over there, and this is same as lambda 1 by lambda 2 integral a to b y1 t y2 bar t dt. And when you see your left hand side, your left hand is also same. You can change the variable here, right? You can write this, it's a dummy variable here, so let me write, because we have here x, let me write x only, lambda 1 by lambda 2 integral a to b y1 of x y2 bar of x dx. Now you take this lambda to that side and shift all the terms on all the terms together, we will get This implies lambda 1 minus lambda 2 integral a to b y1 of x y2 of x bar dx equals to 0. And since lambda 1 not equals to lambda 2 because those are distinct, implies integral a to b y1 x y2 bar of x dx equals to 0, and that is the inner product of y1 and y2 is 0. Hence y1 and y2 are orthogonal. That was your claim. You need to prove that if you have distinct eigenvalues, then the corresponding eigenfunctions are orthogonal, and we have proved it. Next results I will leave as exercise. Let me just state it. Result. You will find this proof in your text. Otherwise, you can check other books. The multiplicity of any non-zero eigenvalue is finite for every symmetric kernel belonging to the class L2. Proof, you see, it is already there in your principal text. So try to prove that, or you can search in some other text as well. Another 3-4 results I will state. Try to prove the sequence of eigenfunctions of a symmetric kernel can be made orthogonal. Second last, the eigenvalues of symmetric L2 kernel. Right. The eigenvalues of symmetric L2 kernel form a finite or infinite sequence lambda n with no finite limit points. So of course you should know what are limit points. No finite limit point. And let me state the last result. Others I will try to prove afterwards. Okay. The result: if lambda 1 is eigenvalue of smallest absolute value of kernel key, then 1 upon mod of lambda 1 will be equals to maximum of mod of inner product a y with y divided by num of y. Right? There are some other results as well. 25. I feel I can prove one result. Let us prove one more result. 10 minutes. The set of eigenvalues, you need to prove all the results. The set of eigenvalues of the second iterated kernel coincides with the set of squares of the eigenvalues of the given kernel. So this is also there. So okay, let us keep this also. Try to prove it. So I have proved 1, 2, 3 statements. Others we can try. We have proved this picture theorem. These results also we have proved. 1, 2, 3, 4, and 5. So I will keep that as exercise. You try to prove the results what we have stated just now, and in the next video we will see the expansion of symmetric kernel. How we can expand the symmetric kernel based on your eigenvalues or eigenfunctions or the iterated kernels.